In this video, we will discuss how we express del operator in cylindrical coordinate. In Cartesian coordinate system, we express del operator like this. The partial derivative with respect to x, then y, then z. But in cylindrical coordinate system, we express del operator with the partial derivative with rho, then with phi, then with z. But here we multiply a factor 1 by rho. Here you see the expression in case of Cartesian coordinate and the expression of del operator in cylindrical coordinate, they are same. That means here you have the three unit vectors I, j, k. Here you have three unit vectors e rho cap, e phi cap, e z cap. But here you have a factor 1 by rho. Why you multiply a factor 1 by rho, we will discuss. In cylindrical coordinate system, you have suppose three coordinates rho, phi and z. Here rho is the radial distance and phi is the azimuthal angle and z is a fixed distance. This height, vertical height, is a fixed distance. And if you draw a perpendicular here, then your x component will be equal to rho cos phi and the y component will be equal to rho sin phi. So x equal to rho cos phi and y equal to rho sin phi, and rho will be equal to x square plus y square square root. And if you find out the tan value, then tan phi will be equal to y divided by x, or phi will be equal to tan inverse y divided by x. These values we will substitute. So you have to remember these values, the values of x, y, rho and phi. To find out the del operator in your cylindrical coordinate, we represent the partial derivative in terms of rho and also in terms of phi, because the point here the coordinate are rho and phi. So you take the partial derivative with respect to rho and also with respect to phi, and you represent the partial derivative of x like this, partial derivative with respect to rho, then partial derivative of rho with respect to x. Similarly, partial derivative with respect to phi, then partial derivative of phi with respect to x. Then we calculate the value of the partial derivative of rho with respect to x and partial derivative of phi with respect to x. Then what will be the partial derivative of rho with respect to x? From geometry I have shown you rho is equal to x square plus y square square root. So if you take the partial derivative with respect to x, then you will find out its value is equal to x divided by x square plus y square square root. It is from the simple derivative with respect to x. From geometry also I have shown you the x value is equal to rho cos phi and x square plus y square square root is equal to rho. So the partial derivative of rho with respect to x is equal to cos phi. Similarly, you have to also calculate the partial derivative of phi with respect to x. From geometry I have shown you phi is equal to tan inverse y by x. So if you take the partial derivative with respect to x, then this will be equal to this much, that is equal to minus y divided by x square plus y square, because you have to apply this derivative rule, that is derivative of tan inverse x with respect to x is equal to 1 by x square. You have to put the value for here, and then you simply write y equal to rho sin phi. I have shown you in the from the geometry of cylindrical coordinate, and x square is equal to, since x is equal to rho sin phi, so x square will be equal to rho square sin square phi, y square will be equal to rho square cos square phi, and you take rho square common, so this will be equal to minus sin phi divided by rho. So we have find out two values. One is the partial derivative of rho with respect to x, this is equal to cos phi, and this is the partial derivative of phi with respect to x, that is equal to minus sin phi divided by rho. So you can calculate the partial derivative with respect to x, that is equal to cos phi, then partial derivative with respect to rho plus minus sin phi divided by rho, then partial derivative with respect to phi. In similar manner, you also calculate the partial derivative with respect to y in terms of rho and phi. So this is the partial derivative with respect to rho, then partial derivative with rho with respect to y. Similarly for phi, and you calculate the value of the partial derivative of rho with respect to y and partial derivative of phi with respect to y. In the similar manner, if when you take the partial derivative of rho, you substitute rho is equal to x square plus y square root from geometry I have shown you, and here you substitute y is equal to rho sin phi divided by rho, then this will be equal to sin phi. So you simply apply the derivative rule here. Similarly, if you calculate the derivative of phi with respect to y, phi is equal to tan inverse y by x from geometry I have shown you, and you apply the same derivative formula of tan inverse x here, and you substitute the value of x square plus y square here, and the value of x, that is rho cos phi, and the value of the partial derivative of phi with respect to y will be equal to cos phi divided by rho. So the various partial derivative with respect to y will be equal to, this is your sin phi derivative of with respect to partial derivative with respect to rho, then cos phi by rho, partial derivative with respect to phi. So in the Cartesian, we write partial derivative with respect to x, y, and z, and unit vectors I, j, I cap, j cap, k cap. And here we have find out the partial derivative with respect to x, this factor, then I cap, plus the partial derivative with respect to y, this factor we have found out, then j cap, and the this k vector, that is z, it is constant, so there is no need to do any change for this factor. Then what you do, you take the I cap, and j cap this side, that means the derivative with partial derivative with respect to rho common from here and from here. If you take common, you have I cap cos phi plus j cap sin phi into partial derivative with respect to rho. Then from these two factors, if you take common partial derivative with respect to phi, then you have minus I cap sin phi plus j cap cos phi divided by rho, and this remains unchanged. And this factor we have deduced in the previous video, that this factor is the unit vector E rho cap, and this factor is the unit vector E phi cap. So you can represent the del operator in terms of rho, phi, and z having unit vectors E rho cap, E phi cap, and Ez cap, and here you have a factor 1 by rho. You see, here you have a factor 1 by rho. That is why you have to write the del operator when you write the in terms of the Cartesian, in terms of the cylindrical coordinate system. When you write the del operator, you multiply a factor 1 by rho in phi here. Okay, so you have to remember the del operator for your cylindrical coordinate system, and this is very useful to you to find out the divergence, gradient, Laplacian in case of cylindrical coordinate system. And in the next video, we'll discuss how you express del operator in spherical coordinate. In spherical coordinate, you have to remember how you express the del operator, so that will be very useful to you to find out the divergence, gradient, and your Laplacian by using spherical coordinate system. This is very simple. If you go in steps, then these things are very simple. So you watch the previous video, and you must have a idea in detail about the three coordinate system, so that there will be no confusion when you deduce the various mathematics in mathematical physics or in while doing physical problems. Thank you.